Okay, so you may be familiar with the computing platforms like CPU, central processing unit, and you know Intel is dominating in this market, and you use that in your computer, laptop. So for example, here Intel has this Core i7, which is a high-end processor. And but nowadays, there are many new computing platforms available beyond the CPU for emerging workloads. For example, GPU is very popular these days for the machine learning. And originally, it was developed for the gaming, right? It's graphic processing unit because the parallelism in the architecture is very suitable for the matrix operations. So then this GPU is very efficient to deal with the graphic kind of processing. But turns out the machine learning and the neural network or like matrix operations. So turns out GPU is very suitable for accelerating the neural networks. So that's why GPU is very popular these days. And furthermore, companies like Google is developing new hardware called the TPU, which is short for Tensor Processing Unit. And this is a very application-specific hardware to accelerate the deep learning for the Google's workloads in the Google Cloud. So you see that the software companies are developing the hardware these days. And many of my friends at Facebook are building the silicon chips, actually, because they want to have their own processor to deal with their own workloads. They don't want to rely on the, let's say, Intel or NVIDIA. They want to build their own chips for their data center, let's say in Google or Facebook. So that's why also software companies are hiring the hardware designers, especially the circuit design, chip design, and people. So I think we will have some guest lectures on the TPU if you are interested in that. So let's talk about the historical trend. How many of you have heard of the Moore's law? Yeah, almost everyone heard this before. So Moore's law is a prediction by Gordon Moore, who is the co-founder of Intel. He made the prediction back in 1960s. And basically he says that the number of transistors on the chip is going to grow exponentially, and roughly the number of transistors will double every 2 years. So this is interpreted as the Moore's law. So it's just a prediction, it's not a law actually. So here is the historical data in terms of the number of transistors on a microprocessor like CPU. So you can see that this is indeed exponential growth. This is in log scale. Okay. And by the way, in this course, we are going to use many of those acronyms for the units. So you need to be familiar with that. K is 1,000. M is million. And this is giga. So you know this is 10 to the power 3. So here is 10 to the power 3. 10 to the power 6 and 10 to the power 9. And here you see that today's processor, let's say Intel's Core i7 or many other processors, for example, from even the smartphone like Apple or A11, A12 processor, the number of transistors exceeds 1 billion already. So on the chip, the number of transistors is larger than 1 billion. This is. So this is Moore's law. And if you are interested in more story about this, you can look at this article in this link. So any questions? And this is more. So the number of transistors double. It is translated to the size of the transistor will reduce by a factor of 0.7 almost every 2 years. So my question is, why 0.7? Any idea? Why 0.7?
Is it just like physical limitations of like how close we can put them together?
Because that's about what the square root of 2 is?
Yeah, exactly. So that's the answer. Because here it says the number of transistors double. Let's say if the chip area is fixed, typically maybe let's say 10 millimeter by 10 millimeter or even smaller than that. Then the number of transistors double, but the total chip area is fixed. That means the size of each transistor will reduce to half per generation, which is about 2 years. So if each device reduced to half of the area of the previous generation, right? So that means if this is 1 and 1, then each device will become 0.7 and 0.7, because if you multiply 0.7 by 0.7 is about half, 50% of the area. So that's why the size of each transistor roughly scale by 0.7x per generation. So this is the original statement by Moore. And here shows the scaling of the size of the transistor. We are going to discuss more about the exact geometry of this device. This is like a transistor. And here the length, this is for the gate. We are going to discuss, have more discussions later. But this is like the representative dimension of this device, and we call the gate length. And here it shows the scaling of that gate length as the year from 1970s. And then here is the dimension of that. In 1970s, it's like 3 micrometer. So which is pretty small actually, micrometer. So micro, how much is a micro?
10 to the negative 6.
Yeah, so in this course you need to do this conversion. So you need to know the micro is like 10 to minus 6 meter if you use SI unit. So then here this is like micrometer, and then this one is actually, let's say, this 0.065 micrometer. Is actually 65 nanometer. So for today's transistor is in the like 10 nanometer scale. And the nanometer, nano is 10 to negative 9. So this is the dimension of the roughly the gate length. So it exponentially decreases. by the factor of 0.7 every generation. So this is historical trend. And here visually, we draw two devices to show you the scaling of the dimensions. So this is at 3 micrometer node. Maybe the device is like this large. And if you scale to today's around like 14 nanometer, then the device is like this, small. So you see the scaling over the years. But I have to say the scaling slows down in the recent 2 or 3 years. If you read the news, for example, Intel lags behind the Moore's law prediction these days because we are reaching the physical limit very soon. So we are going to have some discussions that maybe towards the end of the semester on the advanced technology, why we are hitting the physical limitations and the scaling slows down in the recent few years. But historically, it's like this. Any questions? So why are we interested in the scaling? So, or let's say, in other words, why are the industries, companies motivated to do the scaling? Any idea?
Give more processing power?
Yes. So you have more transistors on the chip, you can do more functionality, you can get better performance. And this is one reason. But the other reason is more important for the industry. That is the cost. Okay. So if you want to sell something, you want to reduce the cost. So if you scale the transistor, on the same chip, you can have more transistors on the same chip. But the cost per transistor will reduce because mostly the, let's say, the fabrication cost will stay the same for the same chip area. But if you have more transistors on the same chip, then the cost per transistor will reduce. So you can lower down the cost, get more functionality, and achieve better performance. For example, faster speed. So that's the benefit of scaling. Any questions? Okay, so let's look at the scaling. And here, typically you see a term called technology node used in the industry to, let's say, stand for a certain tech node. And those are the typical numbers you will see from the literature. And here is the year that this certain technology node is introduced in the industry, for example, by Intel or by TSMC. So we are at 19, and this year TSMC already commercialized 7 nanometer, or well at 2020, of course. Yeah, it's already new year. Okay, so TSMC is, I think, if you read the news, they are going to commercialize 5 nanometer later this 2020, maybe over the summer. So this is the typical number for the tech nodes, and we are really reaching the nanometer scale. So what is actually 1 nanometer? So let's have some comparison in the dimension. Okay. For example, here this is a scale bar for typical dimension. So you know the like a pencil tip here, which you can visually see, is on the order of what? So here the unit is nanometer, and here is 10 to the power 6 nanometer, which is like a millimeter. So like the tip of the pencil is about 1 millimeter, which you can see, okay, by your eye. And then if you scale down this, like the most biomedical, let's say, like the tissue virus cell is on the order of micrometer, okay, which you cannot see. You have to use a microscope to see that. That is on the order of micrometer, okay. And some molecules, okay. If you have few atoms of molecule, then that is on nanometer scale. And then below 1 nanometer, it's really single atom, or let's say very simple molecule like water. So this is, if it's 0.1 nanometer, we also call it angstrom. So typically, one single atom will have a few angstrom. And if your device is like 10 nanometer in dimension, actually you can count how many atoms in that device. For example, if one atom is 3 angstrom, 10 nanometer means 30 atoms from, let's say, this side to the other side of the device, which is pretty small these days. So you see this dimension. So that's why we are hitting the scaling limit, because we really scale the device to the atomic dimension these days. Any questions here? Okay, let's look at some of the real products from the industry. So this is a cross-section of the Intel Broadwell CPU at 14 nanometer load, which was introduced 2014. So this is a cross-section. That means you have a chip, and then you cut, and then you look at the side view, which is cross-section view under the microscope. So you are looking at the side view of the chip. And here you see many layers, actually, many layers. At the very bottom is silicon. And silicon, later we will know that is a semiconductor. So all the chips today are made of silicon substrate. And at the silicon substrate, there will be the building block we discussed earlier, transistor. Okay, so which is very hard to see here actually. So here, this one is one transistor, and we have the zoom in here for that transistor. And most transistor today is called MOSFET. We're going to discuss that later. So MOSFET is short for metal oxide semiconductor field effect transistor. And the last T is transistor. And we will discuss why it's called MOSFET later. But here, this is a single, let's say, transistor. At the very bottom of the chip substrate, you have that transistor. And then the rest of the stack here, can you guess what's that? Any idea? You see many layers. And here, this is metal. All those, let's say, lighter color represent metal. So can you guess what's that? We talk about the three components in the system, right? So what's that? This is interconnect. So we use metal wires to communicate from one transistor to another transistor, or from one circuit module to another circuit module. It's all back end of the NAND, so that is above the substrate. So the transistors is on the substrate, and then you are going to build that communication through the top layer metals, and we call that metal interconnect. And between metals, this darker tunnel here, like this region, is oxide. So, any idea what's the role of the oxide? Why do you need oxide between those metals? For what purpose?
To prevent electricity from flowing between them.
It's basically isolation. So oxide is insulator, so to isolate the signals, because one wire may carry one signal. Maybe you carry 1 or carry 0. Carry 1 means actually that wire is carrying the VDD power supply, and carrying 0 means that it's ground. So here we're looking at the cross section. So those wires actually are pointing in and out of the plane because we cut. So this is an image for the real processor. And here we have some video from Intel to show how you make a chip. So I will have some brief introduction about how you make a chip. So the chip these days is silicon chip, and the substrate, as we discussed, is silicon. But where do you get the silicon? Any idea? Yeah. So the sand has a silicon oxide, but if you purify the silicon out of that, then you get silicon. So that's why in this video it shows you have sand, and then you will purify the sand, and then at high temperature, and extract the silicon out of the sand, and this is called the wafer, by cutting the big cylinder of the silicon. So you are going to cut that cylinder of silicon into those pieces, like your pizza. But this is like, we call it wafer. So the typical dimension for today's wafer is 12 inch. It's 12-inch pizza. Okay, very large pizza, like this large. So this is one wafer, and then it's kind of thin, maybe less than millimeter. So it's a wafer, and then we're going to fabricate the devices on this wafer for many chips. So one wafer will contain maybe thousands of chips, but we are going to fabricate them simultaneously at one time, and later you cut the wafer into small chips. So this is a silicon substrate, and we call it wafer. Okay. And then you get one wafer. Then what you do here is to spin some photoresist, and then do this so-called lithography. We'll have a guest lecture on the fabrication process later. We have more in-depth discussions how you actually make the chip. But here to be simple. So we are going to shine the wafer with some light. And then here you see there's a mask here, and this is the lens. So the mask here basically represents the layout of your chip. like a different region, you have different modules, and then you have the, we just say the wires. You need to define which, let's say, which transistor or which device talk to which device through that wire. But you need to define the physical routing of that wire, and then you make a mask at the very top, which will have that pattern. And then you shine the light through the mask. So some of the, let's say, the light will go through the mask because it has some pattern. Some of the regions are blocked. Some of the regions are transparent. So then you basically use light to transfer the pattern from your mask to your wafer. And then on your wafer, it will have that, let's say, transferred pattern from your mask. So then you use this method to define each region of the wafer. So you need to do this exposure many times, and we call this process as lithography. So you will do this many times, and then you define some pattern on your wafer, and then you need to deposit something. So because in the fabrication process, you see we have metals, we have oxide in that previous image. So that means we have different materials actually on top of the silicon substrate. Your wafer substrate, yes, is silicon, but on top of that, we need to deposit different kinds of materials. And for example, you need to deposit metal or deposit oxide or nitride sometimes. So then you need to do this vapor deposition. So you basically will have something falling down, like your metal atom falling down, and we call this process like deposition.